Hi everyone, welcome back. This is Kilabash. I've been working on this update for quite a while and it's finally ready. Photon 2.2 is the biggest release I've ever made, and it will be the last major feature update for Minecraft 1.21. Instead of simply adding more particle features, I wanted to turn Photon into a complete VFX creation toolkit and a standard for Minecraft. In this video, I'll walk through the major new features and show you how they work. If you're new to Photon, I strongly recommend watching my previous video first. It covers what Photon is and what you can do with it. This video assumes you already have some basic knowledge of the editor, so I'll focus on what's new. At the end, I'll build a small example step by step so you can see how to put these features together. As before, we open the editor with the Photon editor command. At first glance, nothing looks different from 2.15, but thanks to the LDlib2 update, there are a lot of quality of life improvements. You'll notice the panels now dock cleanly into the corners of the view. There's also a new view since Photon 2.2, the timeline. Let me adjust the layout to my preferred setup. I like this arrangement because it's close to the layout I use in Unity, and create an empty project. Let's add a particle emitter so we have something to work with. If you've used Unity or Unreal, the timeline will feel familiar. It lets you animate properties and drive behavior over time, with fine control over anything in your effect. It's especially useful for building prefab-style animations and reusable scheduled patterns. The controls are simple. The top two buttons play the animation and stop it back at frame 0, and you can drag the playhead to scrub to any frame you're interested in. What matters is the Add Track button. You can also right-click the panel to add one. Photon 2.2 ships 8 track types, and I'll go through them one by one. Let's start with the simplest, the activator track. It works just like Unity's. There's a bind field here. Click it, and you're asked to select the target object you want to control, the root node of the hierarchy, or a particle emitter. You can also drag an object straight into it. Double-click the track to generate a clip. You can also right-click and choose Add Clip. The clip defines the range in which the target is active. Delete the clip and nothing happens for the whole timeline. You'll see the object grayed out in the hierarchy because it's inactive. Create a clip, and it's active for the clip's duration. You can adjust the length by dragging the clip edges, or set the duration and start time in the inspector. Clips support copy and paste, multi-select, and dragging. Here's why that's useful. Previously, to delay a particle by 50 ticks, you had to set up delay ticks, or work around it with the emission module, which was awkward. Now you just add a clip. Say the clip starts at frame 50. From 0 to 50, the emitter is inactive, so nothing plays. From 50, it starts emitting. At 100, it's deactivated again. Move on to 150, and it doesn't restart from 0, it continues from the state it had at 100. The period in between is simply skipped. So you can use this to pause an effect and pick it up again later. You can also bind the root instead, which deactivates the root directly, and every child is affected too. Next is the control track. If you know Unity, you'll notice these two tracks are conceptually similar, but behave differently. Let's compare them by muting the activator track. Instead of binding a target through a field, you drag the target object directly onto the control track to create a clip. With a single clip, there's no visible difference. It starts emitting at 50 and stops at 100. But add a second clip and you'll see it restarts from 0 simulation time. That's the distinction. Control track clips replay the effect from the beginning instead of resuming from where it was deactivated. Select a clip and you can set its random seed. With the same seed, the behavior is identical. You can see the particle shapes match between the two clips. Change the seed and the behavior changes. Note, this is a per clip seed for that object as opposed to the global seed. Now let's combine the two. Enable the activator track, bind the particle emitter, and start the control clip at frame 50. The emitter begins simulating at 50, but because it's deactivated, nothing is rendered. The scene looks empty. Around frame 75, it becomes visible, and the particles are already mid-flight because the simulation has been running the whole time. That's essentially a pre-warm. Photon does have a pre-warm option, but you can also achieve it by combining the control and activator tracks, and once the control clip ends, it stops again. The speed track is very handy for time-stop effects. It controls the playback speed of the target object. Drag in the particle emitter, nothing changes yet. Expand the track, and you'll find a curve that sets the emitter's speed. Let's bring it down to 0, then bring it back. Now play it. It speeds up, freezes, and rolls back. You can use this for slash effects or time-stop moments in a fight. You can push the curve much further too. Watch this, that's a lot of emitters. Stop and roll back again. The audio track plays any sound registered in Minecraft. Select the target object to bind as the audio source. We'll use the root. Then double-click to add a clip. Play it, and you'll hear the default sound, the button click. You can drag the clip edges to extend it, and the split lines inside the clip mark each loop of the sound because it repeats for the length of the clip. Select the clip, and the inspector lets you choose the sound by searching. Let's pick the heart sound. The play button previews what's currently selected. Volume is next. You can set it as a plain number or use a curve to get fade in and fade out. Pitch can be curve driven in the same way. You can also set the sound category, which means it respects the player's audio settings. If they disable that category, this sound is disabled too. The last option is 3D attenuation. With it enabled, the volume falls off as you move away from the root FX object and gets louder as you move closer. Attenuation, exactly as the name suggests. Disable it and the volume stays constant for as long as the effect is visible. One thing worth mentioning, some users register sounds through Cube.js, and those may not appear in this list. A sound is only detected if it's registered on both the server and the client. The signal track doesn't affect FX playback at all. It's there to fire events. Double-click to create a marker at a specific frame. Select the marker, and the inspector lets you rename it and attach a sound and custom data. When the effect plays in the world, reaching that frame fires the signal. You can listen for that event from Java code and read the custom data you set here, which lets you trigger your own logic partway through an effect. So this track is designed for the Java API rather than for the visuals, useful when you need to tie your VFX into other systems. The track group is straightforward. Select multiple tracks and drag them into a group. You can reorder them, collapse and expand the group, rename it, and mute or lock the tracks inside. It's a real help once you have a large project with a complicated structure. Last is the animation track, and this one is genuinely powerful. If it's new to you, I'd recommend watching a few Unity tutorials on animation tracks to get the concept. It lets you drive almost any property of an object with an animation curve. For this example, I've created a trail emitter, and I want it to move in a circle. Previously, that wasn't possible from the editor at all. You'd have to write Java code and set the position every frame, which is tedious. Now we can do it directly. Drag the emitter onto the animation track and click Add Property. There's a long list of properties available. Let's start with position. Expand it and you'll see 3 subcurves for X, Y, and Z. Move X out by 10 blocks and play. You can see it working, and the curve shows X moving over time. We can go further with expression clips. The expression field is f of t, where t denotes the time in ticks since the clip started. So let's use sine of t with a radius of 4 blocks and copy the same thing to z as cosine. Play it, that's a circle. A little fast, so let's divide t by 5. Much better. The same applies to rotation, scale, and the rest of the configuration. There's one more feature I want to show, record mode. Select the particle emitter, click the record button, then move the playhead and drag the emitter with the gizmo. Every edit is captured as a keyframe automatically. Stop recording and play it back. The motion is exactly what we dragged. That's a much faster way to author movement. It isn't limited to transforms. Let's try start size. It's fixed at 0.1. And if we raise it, newly spawned particles get bigger from that point on. Color over lifetime works too. That one's a gradient. Double-click to add markers and set colors from white to red. If nothing happens, make sure the module itself is enabled first. Color over lifetime is a gradient sampled by T, so by default every particle shares one gradient. But you can double-click or right-click to create a clip, and that clip represents the gradient over the timeline. Watch what happens. The particles now form a gradient across the whole effect, because the older particles at the top have a higher T, closer to 1, while the newly spawned ones at the bottom are near 0. So you can animate gradients, not just constant colors. And it works for curve properties as well, velocity for example, where you can add a curve clip the same way. The point is that this gives you fine-grained control over properties over time, instead of fixed values. Almost every config is animatable, including GPU data, size over lifetime, physics and shapes, integers and booleans. I strongly recommend trying the animation track yourself. This part is huge, and it's where most of the creative potential in this release lives. That leaves one track we haven't covered, the post-process track. I'll save the details for the shader graph section, but here's a quick look. Create the track, add a clip, and the clip schedules a post-processing effect. There are a lot of built-in effects. Let's try the glitch one. So the post-process track lets you schedule post-processing effects as clips on the timeline. I'll come back to it properly once we've covered shader graphs. Thanks to LDLib2 and Kilograph, we now have a powerful node graph framework for building blueprints and shader graphs in-game, and I've integrated it into Photon. You'll notice 4 new resource types in the Resources panel: shader graph, shader function, full screen graph, and effect graph. Let's start with the first 2. So what is a shader graph? It's widely used in tech art game development. It lets you build a shader visually, with real-time feedback in the editor, without writing a line of code, which is why it's become the standard way to author effects. We've reproduced that in Photon following the Unity 6 standard. Support for Unreal-style conventions may come later. Create a shader graph resource and double-click it. You get a default graph with 2 stages, the vertex stage, which becomes the VSH, and the fragment stage, which becomes the FSH. If you're not familiar with shaders, I'd learn the basics before going further. The default graph gives you a texture node and a sampler, samples the color by the given UV, blends it with the Minecraft fog, and outputs to base color. You can right-click to switch preview modes. Now let's apply it. Create a particle emitter and rename the graph to something memorable. Test graph. One important point, a shader graph is a shader, not a material. So we create a new shader graph material, then select the graph we made. Apply that material to the emitter. Nothing looks different, because the default graph reproduces Photon's default particle shading. So let's change it. Output a color directly to base color, remove the nodes we don't need, and set it to red. Save, and the particles render red. There are plenty of built-in nodes, much like Unity's. One of the most popular is Fresnel. Let's combine it and output to color, and we can route it to alpha as well. If we save now, nothing happens. And the reason is that particles are billboards, always facing the camera. The angle between the normal and the view direction is effectively constant, so Fresnel gives a flat result. To see it properly, switch the render mode to model and render a sphere instead. Make it bigger and reduce the emission rate. Now that looks right. Just like in Unity, we can expose variables through the blackboard. Right-click to create a new variable. This is the same concept as the uniforms and samplers you'd define in a handwritten shader. Let's name it Power. Use it to drive the Fresnel exponent and give it a default of 0.6. Now mark the variable as external. It becomes a fixed input node that acts as a uniform in the shader. Save, then double-click the material we created and reload the shader, and you'll see a value here that lets you adjust power with a reset button to return to the graph default. That's useful when you want one shader reused across several materials with different parameters set per material in the inspector. We can also turn part of a graph into a subgraph. Select the nodes and create a subgraph. It becomes a shader function. Double-click to dive into it, and you'll find the inputs already wired up from your selection. That's a big help when a graph gets complicated. You can break it into layers and manage it much more easily. That brings me to shader functions proper. A shader function lets you author reusable shader logic directly. Let's create one, test shader function. It looks like a normal shader graph, but there's no preview because it has no vertex or fragment stage. Let's build something. Take an input color, mark it as an input, blend it with a purple color, a step node works well here, then output the result. Save it. We've now made a function that blends purple with whatever color you feed it. We can import that function into a shader graph as a node, pass a color in, and take the result out. And if you double-click the imported node and change something, say adjust the value to 1.1, then save, the change propagates to every other graph that uses it. You can also select existing nodes, right-click, convert them into a shader function, and store it in your resources. The full-screen graph is what you use to build post-processing effects. We ship a number of built-ins, invert, and pass-through, for instance, but let's create a new one and call it Test Full Screen. A full-screen graph is similar to a normal shader graph, but with fewer vertex nodes. There's a full-screen position node, which is required, and the output is a color plus alpha. It's a full-screen pass, so there's nothing more to control on the vertex side. In this case, we'll output the sampled scene color directly. Let's make it more interesting. Apply a rotation, feed in a time node so the rotation animates, and output to color. You can see the sampled image rotating with sign of time. Save. So how do we use it? We create an effect graph. An effect graph is the scheduling layer. It defines the order of the passes, how they combine, and the overall workflow of the render. Drag in the full screen graph we just made and connect it to the output. Now, remember the post-process track? Double-click to create a clip, select the effect graph we built, and scrub the timeline to that point. There's the result. We ship a lot of built-in effects, and I'd encourage you to try them. RGB shift, pixelate, dot screen, glitch, bloom, outline, tint, and more. Back in our own full-screen graph, we can append more nodes and chain passes rather than using a single graph. Let's bring in the built-in invert and combine the two. On its own, invert flips the colors of the current frame, but combined with our rotation, we get something more interesting. A rotated, inverted image. And you're not limited to node-based graphs. You can also use handwritten shaders through the custom shader material path, selecting a built-in or your own shader by location and filling in its input parameters. I won't go into that here. It's fairly specialized and assumes shader knowledge, but I'll document it on the wiki. The built-in passes are enough for most cases. Let's play with the glitch effect and save. You can adjust its parameters directly in the graph. You can also use the blackboard to expose a parameter to the clip. Notice the clip has a parameters section. Let's expose intensity, mark it external, and save. Now there's an intensity parameter on the clip, and turning it up gets wild. You can drive that parameter with a curve as well. The curve is sampled across the clip's own progress, from 0 to 1, so you can start at 0, build to a peak, and fade out. You might be wondering what happens if several clips request the same post-processing effect at once. Say this clip sets intensity to 0, and that one sets it to 1. The effect is only executed once, to save performance. And during the overlap, the parameters are interpolated. 0 and 1 give you 0.5. The same idea applies to weight, which behaves like Unreal's. It automatically blends between the scene color and your post-processing effect. Let's switch to invert. It looks like this. Drive the weight with a curve, and now we have a fade in and a fade out. When multiple clips use the same effect, the highest weight wins. The pass is only drawn once per frame, so even with many different VFX using the same effect, it's applied a single time. And Photon applies a blending strategy to decide the parameters and the weight. That holds across every VFX project, not just this timeline, so you don't need to worry about the performance cost. Sometimes, though, you want a clip rendered on its own with its own settings. In that case, enable independent execution. That runs the clip as a separate pass with its own parameters, weight, and mask filter, at the cost of one extra execution. The last post-processing feature is the mask filter. If you've used Unreal, you'll know post-processing materials there can use a depth stencil mask. This is the same idea. By default, a post-processing effect covers the entire screen, so if we apply the outline effect, the ground and the surrounding blocks get outlined too. But what if I only want the outline on my particles? That's what mask filters are for. First, we mark which part of the scene is the mask. Select the particle emitter, go to the renderer section, and enable Write Custom Mask. Give it a mask group name. The name has to be specific and unique because it's shared across different VFX, and every mask with the same name is treated as part of the same group. There's also mask alpha cutoff. By default, at 0, the mask covers the whole rendered geometry. For a billboard, that's the full rectangle. Set it above 0, and the mask is clipped to the sprite shape using the alpha value, which is more precise, but costs more. I'd leave it at 0 unless you need it. To see what the mask actually looks like, there's a debug toggle that shows the mask contents instead of the scene. Now we can use it. Enable mask filter on the post-process clip, and type in the mask group we created. The ground no longer has an outline. The effect applies only to the particles. We can increase the thickness from here as well. So masks let you decide exactly which parts of the scene a post-processing effect applies to. One note, there's a built-in default name that behaves the same as a full-screen effect. There are other mask effects to switch between: the show mask effect, which is great for debugging, and mask outline. The outline is Sobel-based, and I really like it. Combining a mask with the outline is a nice way to get manga or anime-style visuals. As well as exporting a single FX, we now support exporting an FX pack. A lot of people mentioned that distributing an effect was painful. You had to ship the materials, the model files, and everything else alongside it. So we added FX packs. Photon automatically packs everything: the effect references, materials, models, gradients, curves, into a single pack you can hand over directly. Let's export to a pack. Choose the pack, confirm, then name the FX inside the pack. We'll call it Outline. Confirm, and it tells us the FX has been saved into the pack. Don't forget to refresh your resources. And there it is. You can also manage packs through Manage FX Pack. Select a pack you've created and remove an FX from it. And you can export multiple effects into the same pack. FX packs are saved to a specific folder inside your Minecraft directory, the Photon folder, then FX packs. These packs are standard compressed files, so you can open one with 7-zip or a similar tool and see that all the materials are included. I'd recommend packing all of your effects into a single pack, then shipping that pack inside your mod, or simply dropping it into the FX packs folder. It'll be detected and loaded into the game automatically. Since Photon 2.2, we've replaced the old JSON-based model import with a universal mesh input, and you can now import OBJ files directly. Create a new mesh resource and double-click it, and you can choose your model format. There's the JSON model, the same Minecraft format as before, and there's OBJ. If you pick OBJ, you import the file directly with nothing else to set up. Then, in the renderer, you select the mesh you imported, JSON or OBJ, whichever you prefer. And the same mesh input works for the shape module too. Since Photon 2.2.0, we've added GPU instancing, not just for particle emitters, but for trails, beams, and AeroTrail as well. There are two benefits. First, performance. It makes a real difference when you have a lot of trails in the world. Second, it enables additional GPU data, so you can pass per particle data through to the GPU and read it in your shaders. On top of that, we've added custom data, which works the same way as Unity's particle system custom data. It lets you attach extra per particle data, per particle, not per emitter, and read it in your shader. To access it in a shader graph, use the custom data node and set the index to the stream you want. You can define the stream as a vector or a color and pick its time source. Let's use a color and sample it from a gradient. Then output that color directly, though we need to enable GPU instancing first. There we go. So you can push your own data through and read it in the shader, which is very useful for data-driven effects. For the last part of this video, I'm going to show you how to build this effect. Let's take a look first. It's a water ball, and I really like how it turned out. Reproducing it takes quite a few different shader graphs, and it wouldn't be practical to walk you through every one step by step. So I'll focus on building the ball itself, and I'll share the complete shader graphs and the whole project afterwards, so you can go through the rest of the details yourself. Let's start with a new empty FX. First, create a shader. Note that we're creating a shader here, not a material. Rename it to water ball and double-click to open it. Right now, it's just the default shader. Next, create a particle emitter to put a sphere in the world. I'll run through the settings quickly. Emit a single particle, keep it stationary, set the emission rate to 0, and then emit one particle manually. Let's bump the size up a bit. 2 is large enough. Now we swap the model. In the renderer, change the render mode from billboard to model, then pick one of the built-in models, the sphere. Switch to wireframe to confirm it really is a sphere, and pause playback to check. That looks right. The next step is applying our shader to the sphere. Under Materials, create a new shader graph material, double-click to edit it, and select the water ball shader we just made. Then apply that material to the sphere. Let's verify it's actually working. Change the color to something obvious, like red, and save. The sphere turns red, so the whole chain is connected. Now let's work out how to actually build this water effect. Looking at the finished effect, the ball breaks down into 3 parts. A layer of noise flowing diagonally across the surface, a ring of highlight around the rim that bleeds toward the center, and a dissipating edge. We'll rebuild them one at a time, starting with the surface texture. Before that, one habit worth forming. When you're building an effect, put as many parameters as you can onto the blackboard as adjustable variables. It makes tuning enormously easier later. Let's set up a texture sample. Create a variable called noise texture, set its type to sampler 2D, and mark it external so it can be set from outside. Wire it into the sampler node, output the sampled result straight to base color, and save. The texture is now on the sphere. A quick note on where to adjust parameters. You can edit the defaults inside the graph or switch to the Materials Inspector and edit the variables there. Either works. Personally, I prefer editing the material because I don't have to go back into the graph each time. So let's pick the image on the material. I've prepared a noise texture called Noise 3. Let's open it up. That's already close to the rippling water look we want, but we want it to flow, so we need an offset. Drag the offset manually first to see what happens. The texture slides across the surface. Now let's drive that offset with a time node. If we sample the sine of time, the motion is easy to see. The texture scales back and forth. You'll notice a problem here. Once the UV goes above 1 or below 0, the texture breaks. The fix is simple. On the noise texture parameter, set the wrap mode to repeat. It tiles seamlessly, so past 1, it starts again from 0. And because this image is UV continuous to begin with, the seam is invisible. That's exactly the behavior we want. Let's rewire it in a way that's easier to control though. Take the time node into a multiply, times a constant, and turn that constant into a parameter called noise speed, external as well. The important part is setting noise speed to a vector 2. That gives us both directions at once. The X component controls the horizontal scroll speed, the Y component the vertical. Let's try it. Set it to 1 and -1, and there's the result. By the way, nothing was moving a moment ago because the timeline was paused. Resume playback and you can see it flow. We only need 1 channel of the texture here. We don't need 3-channel color. It's really just a brightness map, so taking a single channel gives us essentially the same thing. Let's select these nodes and put them in a group, renamed to central color, so they're easy to find later. Now for the rim. There are 2 ways to do this. We'll use the simpler one, which is Fresnel. Add a Fresnel node and blend it with what we have. That already looks decent. Route it into color and you get a bright ring. It's blown out because adding the 2 together pushes the brightness past 1. But what we actually want is a dark center with the highlight on the outside. So let's do a 1- to invert it. That's closer. Then add a power node and turn the exponent into a new parameter called width to control how wide the rim is. Turn it up and you can see the difference. Higher values make the rim read as wider because the outside gets crushed to black and only the center stays visible. A default of 1 is fine. Since power can push values out of range, we need to normalize here. Let's clamp it back to 0 through 1. Anything above 1 becomes 1, anything below 0 becomes 0. If you want finer control later, you could swap this for a remap, but this is fine for now. Combine that with the earlier add result. That looks good. Let's group this section too. It's worth getting into the habit of organizing as you go. The graph stays much cleaner. Next, the dissipation and coloring along with it. Take the result of the add node and run it through a 1-, which gives us a white rim with a black center. Then add an edge variable and add it in. Edge controls how heavy the border is. Turn it up and the dissipation gets more pronounced. Let's settle on 0.35. Now a remap. Remap takes an input range and maps it linearly onto another range. We'll map 0 through 0.3 onto 0 through 1. An input of 0 stays 0, anything above 0.3 becomes 1, and everything in between is a linear ramp. That's how remap works. Wire it in and save. Now we're getting somewhere. Time to add color. Create a new parameter, set its type to color, expose it, and give it a default of cyan blue. Using it is simple. Multiply it with the clamped result and output that. There's our rim color. You'll notice it still doesn't quite match the final effect because we're missing the glow, and that glow comes from bloom. So let's multiply by a bloom intensity parameter to control how bright the color is. In other words, how many times over it gets amplified. Push it up and the brightness kicks in. That's the look. The rim color is done, so now the center. We want the center to take its color from the particle's own start color. Remember the 1- we did earlier? That gave us the rim. The value going into the add node is the inner core color, so we'll take that directly. Multiply it by the color coming from the particle using a vertex color node. This node has a few modes and you can hover to see the differences. I'll document them on the wiki as well. Briefly, mixed light blends in Minecraft's lighting, so fog affects it, as do skylight and ambient light. Block is affected only by skylight and block light, and color is the vertex color we pass in, which is the start color. We want color here. Before we go further, add a split. The reason is that we'll need the alpha channel later, so it's worth separating color from alpha now. Take the color part into a Vec3, wire it back together, and feed it through so we can see the result. One thing to be aware of. The shader preview can't access the real particle color, so it shows up as white here. After the multiply, blend the two parts together with a lerp and output that to the shader. Let's try a few blend values. 0.5 looks like this, 0.2 like this, and 0.4 gives us something else again. Play it back and you can see the vertex color coming through and driving the center. Other colors are fun too, green for instance, but blue suits this best, and now it really reads as water. Now the dissipation around the edge, which is straightforward. Take the result of that add node into a step node, define a new parameter called step amount, mark it external, and wire it into the step. Step works by setting a threshold and splitting the value in two. Below the threshold goes to black, above it goes to white. What makes step useful here is that we can drive alpha with it directly, which gives us the dissipation. Drag it across, and you can see we've cut the shape out. In the same way, bring in the alpha from the vertex color, multiply it with the step result, and feed that into the alpha output. Fine-tune the parameter a little to taste. And with that, a simple water ball shader is done. Let's add an outline to make it pop. We'll use the built-in outline effect, which gives it a strong anime feel. Then, in the renderer, add a mask and enable Write Custom Mask. You can see the area of the circle that the outline can apply to. Copy the outline and set it on the clip as well. And that looks great. Finally, turn off looping so the particle lasts only 100 ticks, and set the clip to 100 ticks to match. Let's play it back. That's the effect. Now we export it as an FX pack into test pack, for example, saved as waterball. From there, you can use it directly. That's everything for this video. Thanks for watching. If Photon looks interesting to you, come and find us on Discord and GitHub. And from Minecraft 26 onwards, we'll be bringing you an all-new Photon 3, so stay tuned.